Hi everyone, this is John Wen. In today's video, I'm gonna continue to talk about LPOD algorithm. LPOD algorithm, which stands for the Local Path-Based Optimization Scheduling Algorithm, which is proposed by our lab. And in previous video, I briefly talk about the details about LPOD algorithm. And in this video, we will delve into the code implementation in Java of this algorithm. But before that, let's review what we've been talking about for the main strategy in previous video. For LPOD, it's quite similar to ICP-CP. It tries to distribute the deadline on each task as sub-deadlines, and then identify all partial critical paths in the workflow. After all the partial critical paths has been identified, it will try to assign the PCPs to VMs. For every PCP, it tries to make full use of existing virtual machine that satisfy all the task sub-deadline. Then that means it will check every task sequentially and see if there's any virtual machine with a leftover billing cycle that can meet the sub-deadline of this task. If so, the task will be assigned to that virtual machine. Until there's no virtual machine can be found, the rest of the PCP will be assigned to the new virtual machine. After all the tasks have been assigned, it will update the EST, EFT, and LFT for related tasks. Okay, so far I think we understand the basic of LPOD algorithm. Let's delve into the code implementation. So you can see here, this is a LPOD Java code class which extends the workflow planner. So you can see some variables initiate at the very beginning, which we'll be using afterwards for the scheduling. For the function constructor, it takes two inputs. One is a workflow, one is a location as a string. This location is basically a configuration file, a JSON file, which contains information such as the execution part and the task transfer part. For the execution part, it will include the tasks and the respective different type of virtual machine and their execution time. So this is provided at head of scheduling. And for the task transfer, we will have the transfer edges such as a source node and the destination node, as well as the data size on this edge. So we get all the information. You can see there's some tasks has several destinations. That means this task has several child nodes with different data size to transfer on the edge. So let's get back to this main class. After we get this JSON file, we will parse them line by line and put the information into two objects. One is a execution temp object. The other one is a transfer time object. So these two objects will be used in the later scheduling process. So the core meat of this algorithm is still the plan method. So let's get into the plan method directly. So you can see here, for the plan method, firstly, it will do the edge processing for the workflow. So it's quite similar to the ICP-CP. It takes a workflow as input, and then we'll check the task, go through the task in the workflow for the edges. Sorry, we'll go through the edges for the workflows, and then we'll check the source task. If it is null, that means we are getting the entry node, the very beginning entry nodes. We will add the dummy nodes as entry nodes and set the ID as 0. And if the edge does not have destination task, that means we will add a dummy exit node with the ID -1 to the workflow. So otherwise, we're in the middle edges. So we will take the source, we will take the destination, and then we will parse the edge map temp time to the transfer time of these edges. So basically we were getting the time from the object we've already parsed from the JSON file. So let's get back to the plan method, and then we will get the task execution time of this workflow. So basically that's a similar thing. We will get the information from the JSON file by retrieving the data from the execution time temp object. So that will assign the value to the execution time of each task on different type of virtual machine. So let's get back to the plan method. So next step is to calculate priority value. So this is a method called the get priority value. Let's get into this method. Firstly, we will do a topological sorting. Basically, it will check the edges and the dependency on checking, and to try to get nodes, and try to as well as get the, so you can see from here it gets all the parents, and also it will it will check the parents, basically check the dependency relationship, and to line up all the tasks and to sort them in a topological way. And then we will check from the exit node. Basically, you can see here we loop through the topological order size -1 from the end to the beginning, and we will calculate the priority value, because every parent's node priority is based on the child node. We will always get maximum execution time of the child plus a data transfer time. So this is how we calculate the priority value. And then we are going to sort the priority value by using the sort priority value method. Basically that's a, so let's get into this method. So we can see here we are doing the sort by value on the input priority value map. So in this sort by value method, we will add a list of maps instead of maps. So we will do a list of maps and then compare them one by one, and then sort the maps based on the value, the double value. So I think this is this part will do. So let's get back to the code. After we sort the value by priority value, we get a descending order list of the task based on the priority value, and then we have the build task time. So let's get into, we can see that we get all the key sets from the sorted priority value, that means from the beginning till the end, and then we have a order task to array, and we get the size of this initial integer array of tasks, and we put the task time from the beginning till the end, and basically we compute the minimum execution time of the task I, and also we calculate EST for the task I, and we put this information into the temp object, and then put into the task time for the task ith task. So this is how we get the build time task. And then we will find the PCP for the sorting map. So you can see after we get the task time, we will sort the map and find the PCP, because in order to find the PCP, we need to we need to know the execution time as well as the edges weight, or the transfer time. So let's get into this method. Basically, it will add all the ordered tasks into the task list and remove it one by one from the end. So it will try to, I think it's from the beginning. It's from the beginning according to the algorithm, and then to find the child from the list until there's no more child can be found. So it will loop through all the tasks and try to find the task child and then assign them to same PCP until there's no more can be found. So this is how we calculate or find the PCP based on the sorting map. And then we will do the path assignment of the PCP. So here's a core means of this algorithm. Let's get into this method. So basically we'll take paths into and try to assign them, and it will separate into two parts. First part, it will loop through all the tasks in a PCP and try to check the existing virtual machine if that can have the leftover billing cycle and still meet the deadline of this task, and then it will be added until there's no more existing virtual machine can be found that can meet the deadline requirements of any current task. And then the rest of PCP will be assigned to a new virtual machine. So you can see here the rest of the PCP will parse into this method called path assign. So if we're going into, remember in the algorithm, it utilizes dynamic programming, but here we use a list of lists to simulate the TB table. So that means we track from the exit node and that means we calculate from the front of the start node and then calculate every possibility of every node, and then we store it into this TB table, and finally we will trace back and to find the optimal solution. So you can see for the first task in the past, that's what we said. We loop through the task from the beginning, and then we will calculate every possibility or every combination or every type of virtual machine we have, and then to get its the TFT and accumulate cost, as well as the TFT time left. So we will save this information to as a every tuple, and then after we done this, we will do for the here is the first task. We deal with different we will deal with a different formula, but for the second task till the end we will do quite similar but a little bit different, because we will consider if the child node and parent nodes are on the same type of virtual machine, that will associate with different data transfer time. So there will be minor difference, but after all the tasks has been calculated, or the information has been memorized in the TB table, we will try to trace back from the exit node and to always check the smallest accumulate value, and then we will find out the optimal solution. Because the workflow scheduling in the cloud has a feature that we always have a billing cycle to take into consideration. So always take the greedy strategy will not make sure we will have will not guarantee we will have an optimal solution. So that's why we're using the dynamic programming to memorize all the possibilities, and then we can trace back from the exit node to the start node in order to find the optimal solution. So this is a pass assignments. So after the pass has been assigned, we will adjust the EST and the AST, AFT, and also update the successors of all tasks of this PCP and predecessors of all tasks of this PCP. So this is a pass assignment. After this pass assignment have been done, that means all PCPs have been assigned to the virtual machines, and until now all the scheduling has been done. Then we will initiate a global schedule, and then we will check loop through all the virtual machine has been assigned, has been used in the virtual machine pool, and for each of them we will assemble a local schedule, and based on the every task running on the virtual machine, and we will have this local schedule assembled, and in the end we will add every local schedule to the global schedule and to assemble a global schedule, and this is ready to be submitted to the workflow executor for further execution. So until then I think the LPOD has been successfully executed, or the workflow schedule has been successfully output. Next thing is to give this global schedule to any executor, and that can be executed and final result can be output. So I think that's pretty much about this code implementation in Java, which is very similar to the ICPCP code. So if you're interested in, you can refer back to my previous video. You can find a lot of similarity. So I think that's it for today's video. Thank you so much for your time. Until next time, happy coding.